My name is Jeff Utter, and today I'd like to talk about the Aggregator Leaf Tailer pattern and how we use it to bring data to our users with ultra-low latency at theScore. Like I said, I'm a staff software engineer at theScore, which is part of Penn Entertainment, and I've been working on our platform team. I've been writing Elixir for over 6 years, but our project today is a project that we've written in Java. And as you can see, I wrote my first line of Java at age 30-something. I don't know how I made it this far in my career avoiding it, but here we are. I've spent over 4 years working in sports media and betting. And I also lead a double life as a double bassist outside of work. All my formal education is in music, but I've been an engineer for quite some time now. Little outline of what we're going to hit today. We're going to touch on what is the Aggregator Leaf Tailer, our goals at theScore and our constraints around the system that we built. And then we're going to dive into that system named Datadex, a little bit of overview, some architecture, and then how we implement Aggregator Leaf Tailer to meet those goals. And then we're going to have some performance tips, some things we learned along the way building this, and then some conclusion to wrap it up. Okay, Aggregator Leaf Tailer. This term, as a full unit, Aggregator Leaf Tailer, seems to really have been popularized beginning about 2019 by Rockset. They've produced a ton of content, blog articles, talks, white papers on how they use Aggregator Leaf Tailer to build their product. And they're really good, really informational pieces of content. And they seem to be the first people to use Aggregator Leaf Tailer as a package. There's some prior art, a few articles by Facebook and one by LinkedIn. I'm sure there's other ones that describe similar systems and maybe use some of those terms, but they don't necessarily use Aggregator Leaf Tailer as a whole unit. And these are all talks. There'll be links at the end of the slide deck. So what does Aggregator Leaf Tailer look like? It's simply this. There's three main components. The Tailer, which pulls data from various sources, could be Kafka, S3, HTTP APIs, pretty much anything. It then inserts that data into leaves, where the data is stored and indexed. And then on the other side, clients make requests to an aggregator, which pulls the data out of the leaves from one or more leaves, and then does any aggregations or anything that it needs on that data, and returns it to the users. So now on to our goals and our constraints that led us to build the system that we built. We wanted to build a low latency distributed data store that developers actually want to use, and we wanted to build it to access materialized streaming data. To dig in a little bit more, we wanted a system that is low latency, has consistent latency, and here's why. We use GraphQL pretty heavily at theScore, and if you're familiar with GraphQL, you'll know about the data loader pattern. Rather than making a single request to a database with all your joins and pulling back a huge chunk of all of your data at once, the data loader pattern will kind of make tiered requests sequentially, getting more and more information each time. So you may have like a user, the next request may get the user's job, and then the next request may get all the other employees at the job or something like that, but they'll be sequential like that. So consistent latency, especially tail latencies, is really important. If you're making a dozen requests to fulfill one end user request, if one of those takes 10 seconds, you've blown it for your user, regardless of how fast the other ones were. We also want to build something that's has low operational complexity, easy to maintain, easy to deploy. We want something scalable, both horizontally and vertically, and scalable across an organization. theScore has many teams and we're growing quickly. So we wanted something that not only meets the needs of the teams we have now, but teams that we may have in the future. And finally, we want something that is easy for developers to work with. Being that it's sort of a new paradigm to a lot of developers, we want it to be easy so they don't have to go learn a whole new system when they already may have background in something else like RDBMS. We don't want them to have to go relearn all that in a new paradigm. Now, our constraints is maybe where it gets more interesting. Being that we deal with sports betting, every jurisdiction that allows sports betting has their own regulations, and as such, some of them have data locality requirements where certain data can't leave, for example, the state. So we have to operate data centers in those states in order for us to operate. We can't just toss everything in US East 1 and call it good. And therefore, a lot of the managed solutions that make running a fleet of different databases, data stores globally, we can't use them because they don't operate in the specific localities that we need. So kind of throws RDS, Aurora, MongoDB Atlas, all those type of things out the window. We could run them ourselves, but it's a lot of operational overhead. Whereas if we could use the managed solutions, it would certainly be easier. We also then have to contend with our data being geographically distributed. So some of our data can be centralized. For example, sports scores or something like that could be generated in one data center. Then we still need to distribute it out to all of the leafs that have the user's local data. And finally, I've hammered on this a few times, but developer ergonomics is super important. If it's not easy, nobody's going to use it, regardless of how good it is, what we've built. Now I want to touch on kind of a hypothetical ideal architecture. I know as a younger developer, I'd see blog posts and hear talks about evented architectures, and they always sounded something like this to me. You have a bunch of teams working independently. They all publish their data as events onto some kind of bus or queue. Other teams listen to those events, use it to enrich and complete their own data. That keeps your teams decoupled. It's streaming, so it's low latency, yay. And the data is now local, stored in every service, so it's low latency, yay. But there's a lot of shortcomings and drawbacks to this kind of approach that are maybe not obvious up front. There's a ton of hidden coupling, not just in the data shapes. If service A changes, removes a field that service B depends on, then you have a problem. But there's also other constraints around the volume of data and things like that. In addition, each team has to come up with a bespoke way of ingesting that data. They need to know how to go fetch that data, store it in their database. They need a bespoke way of indexing the database. They have to build that all reliably. They're all reinventing the wheel. You can maybe solve some of this with a library, but I don't think that's a complete solution. Furthermore, back to the coupling, if service A all of a sudden is producing 10 times more data because they connected some new third-party external data source or something, well, all their downstream services, dependencies, now have to handle that data, right? That maybe they weren't prepared to scale up their database. Maybe their indexes worked for a small amount of data, but now they have a ton of data they have to cope with. So in conclusion, it's not necessarily the best solution. There's a lot of hidden coupling that you may not realize up front. And lastly, the latency kind of depends on the performance of how each team's implemented this. You may have teams that have plenty of resources and tons of time to coming up with a robust performance solution, but other teams may just have to grab the data however they can and may not have time to really make a reliable and performant way of ingesting and resurfacing this data. So we wanted to build a system where developers can fall into the pit of success. Teams are still going to publish their own data. Nothing's changed there. But we know there's coupling, so we acknowledge it and kind of bring it up front. To get into the details, we use Kafka and we use Kafka schema registry and buff for linting, so we can kind of enforce that nobody's making changes that aren't backwards compatible. And then we want to have a data ingestion system that's uniform and abstracted away from the user, so they don't have to care about how do we connect to Kafka, what do we do when our consumers need to rebalance, how do we get that data into our application reliably. And then to go along with that, we want the indexing system to be similar. We want teams to tell us what indexes they need and then not have to worry about how they're implemented. Lastly, to get that data, we want it exposed through a simple gRPC API. And here's the one trade-off we're making is that the data is no longer local to your application. It's not all in your database and you can't join on it like you can in Postgres or something like that. You have to make a small hop, but we're going to bring that data as close to our users as possible. We want it running in the same cluster and even the same namespace next to the services that are using the data. So that brings us to what we've built. And it's a system called Datadex that looks something like this. There's a lot going on here. We'll break it down. But I wanted to show this slide to kind of emphasize how this can be used in a hub and spoke architecture, which is similar to what we do. You have your spoke, which is every location has their own data center with these components in it. And then the hub may have centralized data that can also be sent down to the spokes. The part of this that's actually Datadex is just really the Tailor Leaf aggregator, but it's showing it in the context of a more full system. So I want to cover the write flow here. Looks something like this. Clients will call backend services to do whatever they need to do. The backend services will process the data as they need, publish their events to Kafka topics, which the Tailor then ingests and stores in the leafs. The read flow, for the read flow, we actually get to delete a bunch of those boxes. We don't even care about the hub anymore. The data is now stored locally in your leaf. So the read flow may look something like this. Clients make a request to some backend service for some data. The backend service calls the aggregator and says, hey, can you fetch me this data? The aggregator reaches out to whatever leaves it needs, pulls the data back in, does its aggregations, and passes it back up through the backend service to the client. Now, I want to mention that our use cases so far at theScore have really been sort of more web application flows. We deal with a lot of data, but maybe not analytical scale of data, analytic scales of data. So that's just something to keep in mind as we continue down our technology stack and how we've built this out. Our tech stack, we use Java, like I mentioned at the start. And the reason for this is really that it has first-class library support for all of the components that we needed to build this out. We use, in the aggregator layer, we use gRPC Java for our clients to talk to us. The Tailor, we're using the Confluent Kafka library, which is, the best Kafka, the most well-supported Kafka library out there. Throughout the system, we're using protocol buffers that get stored in the leaf as protocol buffers and also returned to the client as such. Our storage engine, we're using RocksDB, which has worked out really great for us. We'll talk more about that later. And lastly, I just wanted to mention Kubernetes because in conjunction with a custom Kubernetes operator, it really enables us to simplify our operational complexity. So more into the details, how do we implement the Aggregator Leaf Tailer pattern to meet our goals? For low latency, I said we're using Java, so we're using the ZGC, which is a newish garbage collector. I think it was production ready in JDK 15 around 2020, but it promises sub-millisecond max pause times. Without this, it's really hard or impossible to get your tail latencies down to where we need them. We also are really, really careful with our memory allocations, and this is a topic that'll come up in a little bit as well. And lastly, we do gRPC streaming. This helps us reduce any overhead. There's not headers on every single RPC request, things like that. It's a double-edged sword because it bypasses a lot of the HTTP infrastructure we're familiar with. It kind of prevents you from using load balancers and things like that. So it puts a little bit more work on the client and server side to manage pooling and things like that. But I just wanted to point that out. It's helped us a lot to bring our latencies down, though. For our low operational complexity goal, right now, Datadex is a single code base with 2 deployable units, Datadex itself, and then our Kubernetes operator. The operator allows other teams to kind of define what their Datadex looks like and what data it contains. The operator goes ahead and makes that so. It takes care of backup, snapshotting, scaling, things like that. On the scalability front, we have fast horizontal scale out by using a snapshot backup restore mechanism. We're able to periodically and quickly snapshot the RocksDB database, send it up to some blob storage, and then when we need to add a new node, we pull down that snapshot, and then we only have to recover the last few minutes worth of Kafka data rather than starting over from the beginning of time. Right now, it's a single instance that contains the aggregator, the leaf, and the Tailor. It's been greatly performant for us like that and definitely more simple. I imagine at some point we're going to have to split those out so we can scale them appropriately, but Aggregator Leaf Tailer is kind of designed for that, and we've designed our implementation such that those lines are pretty clear and it should be relatively easy to separate. I'm looking forward to getting to the fun distributed systems challenges that comes with, though. For developer ergonomics, like I mentioned, we're using an operator, so teams just define what their Datadex looks like in a Kubernetes custom resource. We provide an Elixir client that wraps the gRPC client with some niceties. We have a really simple query language, if you can even call it that. On the CRD front, there's a bunch of, this is just like a subset of the CRD, but this is the important part. Teams define the collections that they want to have next to their application. Each collection has a name, in this case game scores, a Kafka topic. So this is the topic where this collection is getting materialized from. Then we have our indexes, and each index has an expression defining the fields in the protobuf that we're using, and then any operators that we need to transform that. On the client side, we call something like this. The first part here is the collection, in this case game scores, followed by the index we want to use. And this bit just kind of fills in the blanks in the index. If we go back to our index, we'll see that the expression was team and date descending. So we're telling it our team is Royals, and we want all the scores that are more recent than the past 7 days. Finally, you have like a little options thing at the end for things like limit. On to performance tips. So these are some tips that we learned building this out that really helped us. The first one, I've mentioned it a few times, but minimizing allocations has been huge in Java. We already reuse buffers for key serialization and deserialization because our keys kind of have a known size. But for values, we implemented an optimization we call fastget. Essentially, we try to reuse a buffer, a small buffer, and we read the value that we're retrieving into that. If it fits, great, we're good. If it doesn't, we then allocate more memory and it's slower. But for a large selection of values, this is actually much faster. And this is just kind of a micro benchmark, so the absolute numbers don't matter. But before this optimization, we were getting about 3,000 requests, read requests a second, and afterwards about 4,000. It's about a 30% increase, which is really good for a certain type of data. RocksDB optimizations, potentially more interesting. And what we've learned here is to ruthlessly narrow our search ranges. And by that, I mean, try to avoid scanning indexes as much as possible. Part of this may be Java specific, but we'll get into like what the indexes actually look like and how that works. In this case, we're handling in queries. So if we were to say like, we want all of the players that are in, where their position is in defensive back or quarterback. An example, we have these two charts. Before the optimization, a certain query was taking over 2 seconds, which is definitely not P99 conf material. But afterwards, we got it down below a millisecond, and I'll show you how that worked out. So this isn't necessarily the query from those metrics, but you could imagine a query like this. You have the player collection, and you're pulling out all the members of the Chiefs by their position, and you only want the defensive backs and the quarterbacks. So the keys in our index look like this. The pipes are just kind of to delineate the sections. Before this optimization, we would end up having to scan the entire index whenever we needed to pull out a subset of the data. The way it would work is we'd read each key out. The key would have to cross the JNI bridge, and then we compare it in Java and say, hey, is this one of the ones that matches our condition? If so, great. If not, we move on. And this can be really slow, especially for a large index. And those JNI bridge crosses can end up allocating memory, which is also slow. So the optimization here is to, rather than have a single query, we execute a couple range queries. We split that up into kind of distinct operations. And RocksDB stores its data on disk sorted. So key lookup is a really fast binary search. But when you need to scan, if you know where you're starting and stopping, you can tell, since the data is sorted, you can tell RocksDB that I need Chiefs who are defensive backs. And it can binary search right to the beginning of that data and read to the end, and then you're done. So rather than reading all the records, we can jump right to the DB records, read them, skip and do another binary search to the quarterback records and read them. We still have to cross the JNI bridge, but only with the data that we actually want. And we don't have to do any comparisons in Java. So our performance takeaways are do less work, allocate less memory dynamically, and scan fewer index entries. That's really helped us out, keep our P99s very, very low. So in conclusion, I just want to say this aggregator leaf Tailer pattern can really help you out in some situations. It's not the solution for everything, but for us, it's really helped normalize stream materialization across our whole organization. Also allows us to have kind of infinitely scalable capacity. Basically, you're limited by how much you want to pay for disk space and a CPU. It's helped us facilitate multi-region replication. Now, there's many ways to do this, but this works well for us. And finally, it helps us achieve those low P99s. And with that, here's a picture of my daughter hugging the ScyllaDB mascot. And I'd like to end my talk, but first I want to say thanks to the organizers of P99Conf and ScyllaDB for organizing this and letting me share what we've learned with you. Also, at the beginning of the talk, I mentioned a bunch of articles and things. So here's all those. I'll leave it up for a second for you to screenshot it if you like, but the deck should be made available afterwards as well. And that's it. If you have any questions, I may have a couple minutes to take them. Otherwise, feel free to reach out, jeff@jeffutter.com or @jeffutter on Twitter. Thanks. I hope you have a nice day.